Welcome, this is EGME-331 Solid Mechanics. In this video, we'll be reviewing the topic of stress-strain diagram. Before we talk about stress-strain diagram, first we need to understand what is a tension test. Tension test is one of the most simple mechanical tests used to determine the properties or the behavior of a material. During tension test, a specimen is pulled with a controlled tensile force, which is equal and opposite force. As the force is increased, the specimen elongates. Based on the load that's applied and the corresponding deformation, we could plot the load deformation plot. However, the load deformation plot has very limited usefulness as far as an engineering application is concerned. The reason being the load deformation plot is specific to that particular sample or the specimen that is subject to the test. A better way to look at things would be to plot the stress-strain diagram, which is derived from the load deformation diagram by converting the load to stress and the elongation to strain. So why is the stress-strain diagram more beneficial than load deformation diagram? It's simply because the stress-strain diagram eliminates the sample specific property, which is the cross-sectional area or the original length of that particular sample, and it's more generalized for a material rather than a specimen. To construct the stress-strain diagram, we take the load deformation data, divide the load by the corresponding cross-sectional area, and the elongation or the deformation by the gauge length. Gauge length is the measure that we take using the extensometer. Plot the stress and strain on vertical and horizontal axis respectively. What we get from the stress-strain diagram is a very useful engineering tool that could explain or give information about the material properties as well as the behavior of the material. We could gather information including the elastic modulus, the yield strength, the ultimate tensile strength, which are extremely useful for engineering calculation purposes. Here we can see a typical stress-strain diagram with stress on the y-axis and the strain on the x-axis. We have two alloys here, aluminum alloy and the low carbon steel. On the stress-strain diagram, we could identify regions or critical points which are of importance. Number one, the elastic behavior or the elastic zone, followed by the plastic zone or the yielding zone. Number two, where the material loses its elasticity. This is followed by an upward phase termed as the strain hardening, where the material becomes stronger, the stress value increases, followed by the highest point on the curve, which is the ultimate tensile strength, number 4. After the material passes number 4, we have a region called necking, where the material's cross-sectional diameter or area decreases, and finally the material fractures. So this is a general stress-strain diagram for two different materials, aluminum alloy and low carbon steel.